When you think about math, it generally feels pretty safe.
Right. Oh, absolutely. Like perfectly contained.
Yeah, exactly. You picture numbers sitting perfectly still on a whiteboard or a clean little graph on your screen. If you mess up, you just, grab an eraser and try again.
Right. The stakes feel entirely academic.
But today, we're looking at what happens when the real world violently rejects a mathematical equation. We're tracing this one tiny, seemingly abstract calculus glitch and looking at how it actually has the power to literally tear a rocket apart in midair.
It's honestly wild to think about.
It really is. We're pulling this from our sources today, specifically this fascinating document called Day 13 Differentiability versus Continuity in Engineering. And our mission for you on this deep dive is to explore how this single mathematical quirk completely dictates the boundaries of your physical and digital reality.
Yeah, we're talking about everything from spaceships in orbit to the AI running on your smartphone.
Exactly.
Yeah.
So let's jump right in. It's a phenomenal topic because we're looking at a fundamental rule of calculus and watching it ripple out across all these completely different engineering disciplines.
You really rarely get to see the exact moment where pure theoretical math just crashes headfirst into the physical limitations of the universe.
Right. So to understand why this happens, we need to unpack two concepts that are like the foundation of this whole discussion: continuity and differentiability.
Yeah, let's lay the groundwork.
So let's set the baseline here for you. Continuity, when you're graphing a function, essentially means you can draw the line without ever lifting your pen from the paper.
Right.
There are no gaps, no jumps, no missing data points.
Right.
But differentiability is about the derivative, which is, the rate of change or the slope of that line.
And this is where the source document highlights a fundamental theorem. Differentiability implies continuity. But continuity does not imply differentiability.
Wait, say that one more time.
So if a line is differentiable, you are mathematically guaranteed it's continuous. But, and this is the trap engineers fall into, you can absolutely have a continuous line that completely fails to be differentiable.
Okay, that feels like a big distinction.
It's massive. Let's look at the mechanics of why that happens. For a function to be differentiable at a specific point, let's just say x equals 0 for simplicity, the derivative has to exist uniquely at that exact spot.
Meaning there's only one right answer.
Exactly. For this to work, the slope of the line coming in from the left-hand derivative must perfectly match the slope of the line going out to the right, the right-hand derivative.
You have to totally converge on the same value.
Right. If they don't agree, the math just breaks.
Which brings us to the classic counterexample from the source, where this convergence just utterly fails, the absolute value function.
Oh yeah, the perfect example.
If you plot the function Sx equals the absolute value of x on a graph, look like a giant letter V, the point of that V rests right at the origin, where x equals 0.
And the graph has no breaks, so the line is perfectly continuous.
Right, you can trace it without lifting your pen.
But that sharp cusp at the bottom, that's where everything falls apart. Because the line forms a sharp corner, the slope coming in from the left is -1, but the slope going out to the right is +1.
Oh, I see. They totally mismatch.
Exactly. Because those two trajectories don't agree, a unique derivative does not exist at x equals 0. Standard calculus completely fails right at that single origin point.
I always think about this in terms of driving a car.
Okay, I like that.
Yeah, so continuity just means the road doesn't have a giant gap in it. You aren't going to drive off a cliff.
Always a plus.
Right. But differentiability means the road curves smoothly. So the absolute value function is like a highway that suddenly takes this exact, sharp, 90-degree V-turn. Yeah, the road is continuous. You won't fall into an abyss, but try taking that mathematically sharp corner at like 60 miles an hour.
Your car's physical limitations are going to become very obvious.
Very quickly. You can't instantly change your momentum like that without snapping the suspension or, blowing out the tires entirely.
And that driving analogy actually scales up beautifully to our first physical domain, aerospace engineering.
Oh, wow. Okay.
Because think about it. If a sharp mathematical corner breaks a sedan on a highway, what does that same structural flaw do to a rocket trajectory flying at Mach 10?
Oh, gosh. That's a terrifying thought.
It really is. In aerospace tracking and guidance systems, the trajectory of a spacecraft must be continuous across several different metrics.
I mean, I'd imagine position is the most obvious one, right? The spacecraft can't just teleport.
Exactly. It has to physically move through space without skipping any coordinates. So the path has to be continuous. Position is what engineers call C0 continuity.
Okay, C0, so the path connects.
The path touches, yes. But as we just established, just because the path is continuous doesn't mean it's smooth.
Right, the absolute value V-turn.
Exactly. A flight computer might generate a perfectly continuous trajectory that happens to include one of those non-differentiable sharp corners. And the computer sees no gaps in the data, so it just attempts to execute the maneuver.
But navigating a sharp corner requires an instantaneous change in direction.
Yes. And in physics, any change in direction is a change in velocity, which means we have to look at the derivative of velocity acceleration.
Which brings us straight back to high school physics, right?
Yeah.
Newton's second law. Force equals mass times acceleration.
Exactly. So if the flight computer demands an instantaneous change in velocity at that sharp corner, it's essentially attempting to execute a maneuver in zero time.
Meaning you divide by 0.
Yes. Mathematically, dividing any change in velocity by a time of 0 results in infinite acceleration.
Okay, wait, so the math is literally demanding infinite force.
It is.
But like, the universe doesn't just politely print a syntax error when you divide by 0. What actually happens to the hardware? You can't just buy an infinite force thruster.
No, you can't. What happens is the physical hardware attempts to obey the mathematical command.
Oh, no.
Yeah. If an autopilot tries to execute that non-differentiable turn, the actuators controlling the flight surfaces or the thrusters, they just slam to their maximum physical limits instantly.
Trying to generate infinite force.
Exactly. They are trying to make a mathematically impossible turn, and the stress of that instantaneous demand causes catastrophic structural failure.
So the spacecraft literally tears itself apart in midair.
It does. Because the physical materials, the titanium, the carbon fiber, they just cannot handle the physical stress of a broken mathematical command.
That is just a terrifying translation from paper to reality. The math demands infinity, and physics responds by ripping the rocket to pieces.
It totally makes sense why an engineer would be terrified of a simple sharp corner on a graph, right?
Oh, absolutely. So how do they fix it?
Well, the source material details how aerospace engineers cannot rely on simple continuous paths. They have to utilize higher-order differentiable splines.
Okay, splines, what does that mean?
They specifically target what's called C-squared or C-infinity continuity. Let's unpack that. We mentioned C0 is just a continuous position.
Right, no teleporting.
Then C1 continuity means the velocity is smooth, meaning the first derivative is continuous. But C-squared means the second derivative, the acceleration, is also perfectly smooth.
Oh, I see. So by guaranteeing C-squared continuity, you ensure that not only does the rocket avoid teleporting, and it avoids instantly changing its speed, but the rate at which it speeds up or slows down is also a smooth curve.
Exactly. It completely eliminates the possibility of demanding infinite force. It fundamentally prevents what engineers call infinite jerks.
Jerk, like the physical sensation.
Yeah. Jerk is actually the mathematical term for the derivative of acceleration. So by forcing the model into a C-squared framework, they mathematically guarantee a survivable flight path before the engines ever even ignite.
That's incredible. Okay, so we've established that a sharp corner in aerospace is a very visible, highly explosive macro-level failure.
Very explosive, yeah.
But the physics completely change when we shrink this glitch down. I want to shift away from massive physical forces and look at the microscopic, invisible world of electricity.
Oh, it's such a great transition.
Yeah.
Because we enter the realm of electronics engineering and signal processing here.
And the scale is way smaller, but the mathematical villain is identical, right?
It's completely identical. In this domain, we're dealing with electrical circuits, specifically switching elements and signal generators that process voltage waveforms over time.
And a great example from the document is the perfect triangular wave.
Yes. If you visualize a triangular wave on a monitor, it just looks like a continuous zigzag.
Right. The voltage ramps up steadily, hits a peak, and then immediately ramps down steadily. It forms a sharp point at the top.
Just like our absolute value graph.
Exactly like it.
At that exact turnaround point where the positive voltage ramp switches to a negative ramp, the function is unbroken. There are no gaps in the electrical flow, but it's non-differentiable.
We have our sharp corner again.
We do. And to understand why this is a problem, we have to look at how different electrical components interact with that wave. The source specifically brings up ideal inductors and capacitors.
Okay, let's define an ideal inductor for a second for the listener. It's a theoretical component that perfectly resists any changes in electrical current.
Right. And the governing equation for an inductor dictates that the voltage across it is strictly proportional to the rate of change, the derivative of the current passing through it.
And for a capacitor?
For a capacitor, it's the opposite. The current is proportional to the derivative of the voltage. But in both cases, the physical behavior of the component relies directly on evaluating a mathematical derivative.
So when you feed that perfectly continuous triangular waves into the inductor, the component hits that sharp peak. And the math demands a derivative that does not exist smoothly.
Exactly. The sharp corner forces a massive disruptive step change. It demands a sudden discontinuity in the current or the voltage.
The circuit is essentially being forced to try and execute an instantaneous change in its electrical state.
Right, which is impossible.
So earlier we used an analogy of dropping a heavy box to explain electromagnetic interference, but that doesn't really capture the physics of what you're describing
I
here.
don't know, it's a bit clunky.
Think about it like a digital audio speaker trying to play that sharp triangle wave. The physical speaker cone moves out smoothly as the voltage ramps up.
Okay, follow you.
But at the exact peak of the triangle, the wave demands that the cone instantly reverse direction and move inward in zero time.
Right, and a physical speaker cone has mass, it has momentum, it cannot instantly reverse direction in zero time.
Exactly. So when the magnet tries to force it to snap back instantly, the cone flexes, it ripples, it vibrates chaotically trying to obey this literally impossible command.
Wow.
Instead of a clean tone, you hear a harsh broadband crackle or hiss layered over the sound. Those chaotic extra vibrations are the high-frequency harmonics.
That is a brilliant way to visualize it, because that translates perfectly back to the electrical domain. The sharp, non-differentiable points in the voltage wave create infinite high-frequency harmonics.
And the source highlights a really crucial detail here about the Fourier series.
Yes, the Fourier series decay for this specific triangular wave is proportional to 1 over n squared, where n is the harmonic number.
We really need to explain why that specific decay rate is so problematic.
So in signal processing, you want the power of high-frequency harmonics to decay or drop off as quickly as possible.
Right, you want them to fade out.
Exactly. If a wave is perfectly smooth, the high frequencies decay incredibly fast, maybe at a rate of 1 over n to the fourth. They practically vanish.
Okay.
But a rate of 1 over n squared, that is considered an incredibly slow decay in this field.
Meaning those chaotic, ultra-high frequencies stay loud. They don't fade out fast enough at all.
Because they don't fade out, they literally bleed into adjacent circuits. That is what electromagnetic interference, or EMI, actually is.
Oh, wow. So the mathematical sharp corner translates physically into intense electrical noise.
Yes. It wreaks havoc in high-speed digital systems. It can scramble data packets, it can cause critical communications to fail, or make a delicate sensor register phantom readings.
It's basically digital static blasting everything around it.
Exactly. Engineers are literally forced to design complex low-pass filters specifically to smooth out those waveforms. They effectively round off the sharp corners so the circuit doesn't drown itself in its own mathematical shockwaves.
It is genuinely fascinating.
Yeah.
Like a titanium rocket snapping in half and a delicate circuit board drowning in static are both caused by the exact same failure of a left-hand and right-hand slope to converge.
It's the same math.
And aerospace and electronics engineers spend massive amounts of time and money actively filtering out, designing around, and just avoiding these non-differentiable sharp corners at all costs.
Which brings us to a massive paradox in the engineering world.
The machine learning stuff.
Yes. Because in the realm of computing and deep learning, software engineers do the exact opposite. They intentionally build the architecture of modern artificial intelligence directly on top of one of these non-differentiable corners.
I found this to be the most surprising part of the whole source document. We're talking about the foundational logic of the systems running facial recognition, large language models, autonomous vehicles.
Yeah, all of it. Modern deep learning architectures rely on a process called backpropagation to train their neural networks.
And backpropagation is essentially a massive engine of gradient-based optimization, right?
Right. It uses calculus-specifically derivatives to adjust its internal weights and learn over time. It measures the slope of the error curve to figure out how to improve itself.
But the most common activation function used inside these neural networks is something called the rectified linear unit, or ReLU.
And the formula for ReLU is almost deceptively simple. The document defines it as the function fx equals the maximum of either 0 or x.
So if the input number is negative, the function just simply outputs 0. It draws a flat line.
Exactly. But the moment the input hits 0 and turns positive, The function outputs that exact positive number. It ramps up in a perfectly straight line at a 45-degree angle.
So structurally, it is literally just a shifted version of our absolute value function.
It is, which means it has a sharp corner exactly at x equals 0.
The line is continuous, but
Yeah.
it is fundamentally non-differentiable at that exact point.
Yes, the most advanced learning systems on the planet are deliberately built on a mathematical glitch.
That is just wild, because every time the AI evaluates a data point at exactly 0, standard calculus fails. The unique derivative doesn't exist.
It doesn't.
So if the entire neural network relies on calculus-based gradients to learn, and the calculus breaks at 0, how does the AI not just immediately crash?
That's the million-dollar question.
Right. How does the software not experience the digital equivalent of a rocket tearing itself apart due to an infinite value?
Well, software engineers bypass the physics entirely by using a concept called subgradient calculus.
Subgradient calculus. Okay.
Yeah. Because they operate in a purely digital domain, they can essentially just hack the math.
What do you mean hack it?
When the AI is running its backpropagation loops and it hits that exact non-differentiable boundary of x equals 0, it doesn't try to solve the impossible equation. Instead, the derivative is artificially assigned a structural placeholder value.
Wait, they just make up a number to bridge the gap?
Pretty much. In the underlying code of massive frameworks like PyTorch or TensorFlow, they typically assign the derivative at that exact sharp corner a hard-coded value of exactly 0, or sometimes 0.5.
That's hilarious. They're literally just paving over the glitch.
Totally. They essentially tell the system, hey, don't worry about the math here, just pretend the slope is 0 and keep moving.
It's purely pragmatic.
Exactly. By forcing that artificial placeholder value, they prevent runtime exceptions that would instantly crash the program. But more importantly, it stops a phenomenon known as gradient explosion.
Gradient explosion. I assume that's the digital equivalent of our infinite acceleration problem in aerospace.
Very similar, yeah. If the optimization loop tries to divide by values approaching 0 without a defined limit, the mathematical error just spirals completely out of control.
Generating infinitely large numbers.
Right. Which corrupts the entire neural network instantly. The artificial subgradient prevents that infinite spiral from ever happening.
It just paves over the mathematical impossibility.
And it works flawlessly. It allows the neural network to train incredibly fast, which is exactly why ReLU remains the industry standard today, despite its glaring theoretical flaw.
That's amazing. You know, it makes you wonder how engineers even identify these invisible traps in the first place.
It's not easy.
I mean, we're talking about theoretical glitches hidden deep within complex algorithms or high-frequency waveforms. A structural engineer can just look at a blueprint and see a weak support beam, but how do you visually see a mathematical failure before it destroys a satellite or crashes an AI?
This relies entirely on computational proof. The source document gives us some really great insight into how engineers use specific Python libraries to visualize and mathematically prove exactly where the math breaks down.
They use a library called SIMPy, right? Which handles symbolic mathematics.
Yes. And we really need to distinguish between symbolic math and numerical approximation here.
Right, because if you just tell a standard computer program to evaluate the slope at 0, it might just check a tiny number slightly to the left, like negative 0.001, and a tiny number to the right.
Exactly. And standard floating point math on a computer is imprecise. If a purely numerical engine averages the points around that absolute value cusp, it might erroneously calculate a slope of 0.
Completely hiding the structural anomaly.
It misses the danger entirely just due to rounding errors.
But SIMPy doesn't crunch decimal approximations.
No, SIMPy evaluates an equation algebraically using the strict, rigorous rules of mathematics.
So it doesn't guess.
Never. When an engineer feeds the absolute value function into SIMPy and asks for the derivative, it logically concludes that the derivative is the value of x divided by the absolute value of x.
And that equation mathematically exposes the undefined state right at 0.
Yes. It outputs what the source refers to as the signum function.
Oh, the signum function. I saw that.
Yeah, it essentially extracts the sign of a real number. It outputs a stark -1 for anything below 0, a +1 for anything above 0, and flags the origin as an issue.
So it explicitly reveals the mismatched left-hand and right-hand slopes that numerical approximations would just completely gloss over.
Exactly. And once SIMPy isolates that algebraic truth,
Yeah.
engineers can use libraries like NumPy to handle the heavy arrays and matplotlib to plot those functions visually on a screen.
They can actually map the continuous function and directly overlay the broken derivative on top of it.
Right, proving with hard data exactly where the physics will fail.
It is such a powerful visualization. It really highlights how theoretical concepts from like a freshman calculus textbook are the literal blueprints governing the stability of our physical and digital infrastructure.
It's all connected.
It really is. So we started this deep dive exploring a surprisingly simple rule that continuity does not guarantee differentiability. A path can be unbroken, but still harbor a mathematically jagged edge.
A very dangerous edge.
Yes. We traced how that single anomaly echoes across vastly different scales of reality. It explains the physics of why you can't force a spacecraft into an instantaneous turn without demanding infinite force and suffering catastrophic destruction.
And it reveals why sharp electrical pulses refuse to decay quietly.
Right, instead generating that chaotic, slow-fading, high-frequency noise that disrupts digital systems. And perhaps most surprisingly, it exposes the incredibly clever, pragmatic hacks that software engineers utilize to build the world's most advanced AI right on top of an equation that technically should not work.
And you know, that AI application leaves us with a really compelling thought to consider. Yeah. We explored how computer scientists artificially assign a placeholder value, a hard-coded 0 or zero point 0.5, to completely bypass a fundamental calculus failure at the heart of neural network training.
Right, they just patch it.
They essentially apply a digital patch over a mathematical impossibility to keep the system moving forward. But if the foundational architecture of the world's most advanced decision-making artificial intelligence is held together by mathematically paving over a glitch with an artificial placeholder,
Oh, I see where you're going with this.
it invites a much larger question. What other structural blind spots or pragmatic hacks might be hidden deep within the code that runs our modern world?
Wow.
Things that are silently shaping the logic of the systems we literally rely on every single day.
That is a fascinating and honestly slightly unnerving angle to consider. The next time you picture math as just harmless abstract numbers sitting safely on a whiteboard, remember the sharp corners.
Definitely remember the
Yeah.
corners.
Remember what happens when the real world violently pushes back against the equations. Thank you for joining us on this custom deep dive into your sources. We'll see you next time.